Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Principles of Cake Filtration. So, in cake filtration we have seen there is a kind of filter medium onto which normal to the surface of the filter medium the slurry is allowed to pass through, and then whatever the big coarse particles, large amount of coarse particles are there, they will be forming a kind of a layer which forms a kind of a layer of particles which is known as a kind of cake formation. So under such conditions, what are the working principles, etc., those things we are going to develop now. Before going to develop those working principles, we will see how this cake filtration process can be related to packed bed, flow through packed bed that we have already seen one of the previous lectures. Principles of cake filtration. The principles of these cake filtrations are almost analogous to the case of flow through packed bed or fixed bed or kind of flow through porous media. But in the case of packed bed or porous media or fixed bed, what happens, the resistance to the flow whatever is there, that is independent of the time, that does not depend on the time. Okay. So, but whereas in the case of cake filtration process, whatever the cake is there, that cake is actually behaving as a kind of a packed bed now. So, that size of that cake is gradually increasing with the time. So, more and more particles are coming and then accumulating on the surface. So, cake thickness is increasing. So, obviously the resistance gradually increases. So, that means here in the case of cake filtration, the resistance to the flow through bed of particles that is forming cake is a kind of function of time, and in this resistance increases with the increasing the filtration process time. So, just to recapitulate what we have this kind of a filter medium in the for a cake filtration kind of thing. So, here it is having some kind of a porous structure. These porous structures are shown almost kind of channels kind of thing, straight or slightly straight channels kind of thing, but not necessarily they will be a straight channels. They can be a kind of interlinking between the channels, etc. The slurry comes through here in the normal direction to the surface of the filter medium, right. So, the large amount of solid particles or whatever are there in the slurry, they will be deposited on the filter medium, and then they will form a kind of cake, and then that cake size gradually increases as the filtration time increases. Thus, the resistance to flow will also increase. So, whatever the clear or almost clear filtrate is there, that will be collected from the bottom. So, now what we have to do, we have to see how the principles of packed bed are that we have already developed, how we can make use of those principles for the case of cake filtration. Basically, the Ergun equation or Kozny-Karman equation, whatever or Burke-Plummer equation for different cases are there. So, how we can make use, actually if the flow is small, low Reynolds number flow, then Kozny-Karman equation is valid. If the flow is high in the Newton's flow regime, then kind of Burke-Plummer equation is valid. If you add the both the resistance together, then whatever the equations that you get, that is known as the Ergun equation, right. So, those equations or any of those equations can we make use here or not, that is what we are going to see, and then how to modify to those equations for a given cake filtration problem here, right. So, in cake filtration, resistance to flow increases, as I mentioned, with time as filter medium becomes clogged or filter cake builds up. So, thus whatever the Ergun equation is there, that should be modified accordingly to bring in the effect of the filtration time or cake formation or clogging of filter medium or building of cake, whatever the reasons are there. So, how to bring those concepts here. So, all of them can be combined together if you can bring in the time factor into this equation. So, that is what we are going to see. Once you bring the time factor into this principles of flow through packed bed cases, whatever the equations are there, in those equations if you bring in the time factor, so then accordingly the rest other things will also automatically come into the picture. How do they come, that we are going to see now. So, in this cake filtration, what are the important parameters of interest? Obviously, we have seen that the filtrate, the volumetric flow rate, and then resistance to the flow, that is the pressure drop, and that increases, right, that pressure drop increases with time. So, these are the kind of two important things. So, these are flow rate through the filter and pressure drop across the unit. Okay. And then as the time of filtration increases, what happens, as I mentioned, the more and more number of particles are deposited on the filter medium, and then building up a kind of cake, or cake thickness increases. So, accordingly the filtrate volumetric flow rate of the filtrate that we collect from the other side of the filter medium, that decreases, or the pressure increases in order to maintain the flow, the volumetric flow rate of a filtrate. So, that is either of the two cases happens, one is the flow rate decreases or pressure drop increases. Now, since having these two important things are happening, that is either flow rate increasing or pressure drop is decreasing. So, then it is possible that these filtration processes may be operated in two such conditions. In one conditions where you can maintain the constant pressure and then let the volumetric flow rate to decrease with respect to the time, or you gradually increase the pressure drop in order to maintain the constant flow rate of the filtrate. So, that the gradual increase in delta P with respect to the filtration time is a kind of a very rare case. So, these two things are possible. In constant pressure filtration, the pressure drop is held constant and flow rate allowed to fall with time. In constant rate filtration, that is constant volumetric filtration rate, if you maintain constant volumetric filtration rate, the pressure drop is progressively increases to give constant filtration rate, but however, this is a very rare case. So, in cake filtration, the liquid passes through two resistance. One is the whatever the filter medium is there, that resistance offered by the filter medium as it is, and then another one is that as the time progresses, these particles are depositing on the surface of the filter medium and then forming a kind of a cake. So, there are two resistance. The one resistance is the filter medium resistance, another one is a kind of resistance due to the cake formation, or cake resistance. These two resistance are possible in general in a given cake filtration process, that is resistance because of formation of cake and then resistance of filter medium. So, one should have a kind of information about what is this resistance due to the formation of cake, or cake resistance, what is this filter medium resistance. We need to have some kind of information, or we should develop a kind of equation, so that by using some experimental information we can calculate this resistance for a given situation where cake filtration is taking place. In general, filter medium resistance is normally important only during the early stages of the cake filtration, because what happens as the time of filtration gradually increases, more and more number of particles are depositing on the surface of the filter medium, and those particles are forming a kind of cake, and that cake is offering much more resistance compared to the whatever the filter medium resistance is there. So, whatever the filter medium resistance is there, that is going to be having a kind of importance only at early stage of filtration processes, where the cake formation is not there, or it is almost a kind of a minimum cake formation or negligible cake formation is there at early stages. Under those early stages of filtration processes only, this filter medium resistance is a kind of important one. Cake filtration is obviously 0 at the start of filtration, because at the start of filtration there is no kind of particle depositing on the surface of the filter medium. So, there is no cake formation. So, there will not be a kind of any kind of a cake resistance, but as the filtration time progresses, more and more number of particles are forming, and then gradually the cake thickness increases, hence the cake resistance also gradually increases with time as the filtration proceeds. if cake is washed after it is filtered, both resistance are constant during the washing period in general, and that of the filter medium is usually negligible compared to the resistance of whatever the cake formation. Due to the cake formation, whatever the resistance is there, that is compared to the cake resistance, the filter medium resistance is in general negligible, especially when cake is washed after the filtration. Now, what we understand from here, there are two resistance. So, then obviously there will be a kind of two pressure drops. So, the overall pressure drop at any time is going to be sum of pressure drops over the filter medium and across the cake formed, that cake formation or whatever the cake has formed, across that cake formed, whatever the pressure drop is that one, plus the pressure drop across the filter medium, whatever the pressure drop is there, these two pressure drop when you add together, then you will get the overall pressure drop for that given cake filtration system at any given time. So, because what we understand, this overall pressure drop is also gradually increasing because of gradually cake formation or the thickness of cake is increasing, or the more number of particles are being deposited on the surface of the filter medium. So, this overall pressure drop is gradually increasing with time, right. So, but at particular specific time, if you take if you have a kind of pictorial representation of these pressure drops, then you can have like this, right. So, this is the kind of filter medium that we have, and then slurry is coming down in this direction, okay. Slurry is coming in this direction, right, and there is a kind of a cake formation, and then whatever this cake is there, that cake is a kind of a form like this kind of cake, whatever this LC is represented here is a kind of thickness of the cake that has formed. Usually you do not have a kind of sharp interface like this, but in general for a representation we can have a kind of sharp interface between the slurry and then first layer, top layer of the cake, okay. So, these are all a kind of particles that are being deposited on the surface of this filter medium, right. So, now these particles are almost a kind of accumulated, and then they are a kind of in a packed condition, and then they will be behaving almost like a kind of a packed bed, okay. So, now here what we see, the pressure at the top surface of the cake, whatever is there, that we call it PA, let us take it as PA, and then pressure downstream in the filtrate side, whatever the pressure is there, let us call it PB, and then there is one more pressure that is different from PA and PB. So, that pressure is at the on the surface of this filter medium, and then it is in between this, or at the interface between the filter medium and then cake formed, whatever is there, that pressure is known as the P prime, right. So, what we can see here, so the pressure drop is a kind of a non-linear behavior we can see here, because the different size of particles in general will be there, and then when these particles and are kind of packed as a kind of cake or the kind of bed of particles, then whatever the fluid is coming, because of that one this packing structure may keep changing, and then voids may be keep changing from one layer of the cake to the other layer. If you divide this cake into the separate layers, n number of layers like this, each layer of the this cake is going to have a different properties in general, but however we try to avoid such kind of complications, right. That is one reason. Another reason is that the on the filter medium surface, whatever the particles are there, they will be having a kind of experience a kind of largest compressive forces, and then compared to that one, the other sides, the compressive forces are towards the slurry side. As we move away from the filter medium towards the slurry side, that compressive forces gradually decreases, and then because of those reasons also sometimes it is possible that pressure drop, that we are going to have a kind of non-linear pressure drop. So, the question may be there that why it cannot be a kind of linear pressure drop between these two, because of these many complicated things like the size of the particles, because the particles are not same size particles, right. Shape of the particles is also not same, and then the voidage of the each individual layer, if you break this cake into different layers, so that voidage is also going to change from one layer to one layer in general. So because of those many reasons, the pressure drop is going to be kind of non-linear. There are other reasons also, like compressive force is a kind of a maximum at the filter medium surface, and then it gradually decreases as we move towards the slurry from the filter surface through the cake. So now here what we see, the pressure drop in the cake is what? Is nothing but Pa minus P prime, and then pressure drop across the filter medium is nothing but P prime minus Pb. So let Pa is the inlet pressure, Pa is the inlet pressure, that is the upstream side of the cake, the top layer of the cake, that is whatever is there. So at that layer pressure is Pa, and then Pb is the outlet pressure, that is at the filtrate size, whatever the pressure is there, that is Pb, and then P prime is pressure at bottom boundary between cake and then medium, whatever at the interface between the filter medium and cake is there, at that interface the pressure is P prime, right. So Pa you can measure, Pb you can measure in general for experimentally if you wanted to measure by some means, but P prime is not possible to measure in general so easily. So that is the reason what we can write, overall the pressure delta P as a Pa minus Pb, that is nothing but Pa minus P prime plus P prime minus Pb, so that you can avoid calculating this P prime, and then without that you can get the overall pressure drop. However, this Pa minus P prime is nothing but the pressure drop across the filter, and then P prime minus Pb is nothing but the pressure drop across the filter medium. So that if you noted delta Pc and delta Pm respectively, so delta P is equals to delta Pc plus delta Pm respectively. So then where delta Pc, delta Pm are nothing but pressure drop across the cake and then across the filter medium. Now you wanted to calculate this pressure drop through the filter cake, because this pressure drop equation for now this cake is behaving as a kind of almost kind of a packed bed kind of thing, and then for the packed bed pressure drop equations you are having. So one way or other way you can make use of that flow through packed bed cases, for which whatever the pressure drop equation is there, that equation you can use here and then modify for this kind of problem, for the current situation of the problem where cake formation is there and then cake thickness gradually increases, because of which pressure drop gradually increases. For that situation you can make use of this equation. So that is what we are going to do now here. So let us take the same picture once again here, but now what we do within this cake thickness is Lc, right. So we have this filter medium, right, and then there is a kind of cake formation. The cake thickness at certain instant of time, it is going to change with time, but we are taking at one particular instant of time the thickness of this cake is Lc. The pressures as already discussed Pa and Pb at either extremes of cake top surface and then filtrate side respectively. P prime is the pressure at the interface between filter medium and then cake. So now within this Lc cake, what you do, you take a particular location at a distance L from the filter medium, the distance L from the filter medium you take, and then further please be noted this Lc is measured from the filter medium side, So Lc is initially 0 at the filter medium, and gradually as time increases that Lc gradually increases from filter medium side towards the slurry side, that particles being deposited, right. So now at location L within this cake you take a kind of a thin layer of whatever the cake that has formed. So one small layer of that cake you take, whose thickness is kind of a dl, right. So now the corresponding pressure for this layer of cake that we have taken is P, right. So pressure drop for this layer of cake that has been sliced out of the overall cake of thickness LC is there. So, overall cake thickness LC, from out of which we take a kind of a slice of cake at distance L from the filter surface filter medium surface, and then the thickness of this slice of layer of this cake is dl. So, the pressure is for this layer is P. So, for across this layer, now this layer is a kind of maybe thin layer of thickness dl, but across dl there is a pressure drop, right. That pressure drop you can calculate using the Kuznets-Karman equation. Okay. So, consider a section through a filter cake and filter medium at a definite time t from the start of flow of filtrate as shown in the figure. Corresponding thickness of cake measured from the surface of filter medium is LC at this time t. Okay, this is at particular time t, whatever the picture we have shown. A is the filter area measured perpendicular to the direction of flow, normal to the direction of flow, whatever the surface area, the area of exposed of the filter medium area that is exposed for the separation or for the filtration process is A. Consider a thin layer of cake of thickness dl lying in the cake at a distance L from filter medium, and then corresponding pressure at this layer is P, right. Then this layer consists of thin bed of solid particles through which filtrate is flowing. So, in this filter bed the velocity is sufficiently low. Usually in filtration process the volumetric flow rate of filtrate is in generally small enough to consider that the flow is in a kind of a laminar flow region, right. So, the same we can apply here for this layer of cake for which the velocity is sufficiently low, so that we can make sure, so that we can ensure that laminar flow is the laminar flow conditions are existing for this layer of the particles. So, in this filter bed the velocity is sufficiently low to ensure the laminar flow, and then if superficial velocity of filtrate is u, that using the Kuznets-Karman equation for low Reynolds number flows, we have this dP by dl is equals to 150 mu u 1 minus epsilon whole square by pi s square dP square epsilon cube. Mu is the viscosity of the filtrate, u is the superficial velocity of filtrate, epsilon is the voidage of the cake, pi s is the shape factor of the particles that are forming the cake, and dP is the nominal diameter of the particles which are forming the cake. Epsilon is anyway the voidage of the cake that we have already seen. This equation we can modify it. So, because of lower cake porosity near filter medium across the cake layer, the pressure gradient is in general nonlinear. So, because of lower cake porosity near filter medium across the cake layer, the pressure gradient is nonlinear. Now, in this equation wherever pi s dP is there, you can substitute 6 Vp by Sp, because we have already seen this pi s is nothing but 6 by dP divided by Sp by Vp. So, 6 Vp by Sp, if you write in place of pi s dP in that above equation, the same equation will be written as a kind of 4.17 mu u 1 minus epsilon whole square, and then pi s dP is nothing but 6 Vp by Sp. So, that we can write Sp by Vp whole square on the numerator side, okay, and then epsilon cube is anyway. So, here what we had, actually this equation what we had 150 mu u 1 minus epsilon whole square pi s square dP square, right. So, that we have now here 36 Vp by Sp whole square and then epsilon cube. So, this is nothing but pi s square dP square. So, in place of pi s square dP square we are writing 36 Vp by Sp whole square. So, that we rearrange. So, you are having this equation, right. 150 by 36 is kind of 4.17, right. Here dP by dL is the pressure gradient at thickness L, mu is the viscosity of the filtrate, u is the linear velocity of filtrate based on the filter area, and then Sp is surface area of single particle, Vp is volume of single particle, right. So, but these equations in general and then epsilon is the porosity or the voidage of the cake. But this equation here whatever we have taken, so that is taken for a kind of single particle basis on single particle, say surface area of single particle, surface area of volume of a single particle, etc. Right. So, but in general the suspension is made up of kind of several different types of particles, different size, different shapes are there, right. Superficial velocity of filtrate based on filter area can be given as volumetric flow rate of filtrate per unit filter area. So, now the so called time factor is coming into the picture in this pressure drop equation now. So, that is U is equals to dV by dt by A. dV by dt is nothing but volumetric flow rate of filtrate, and then you divide it by filter medium area which is exposed for the filtration, then you will get a kind of a whatever the superficial velocity of the filtrate. Okay. So, now this if you substitute in that equation 2, you will get a different equation. So, here in this equation V is the volume of filtrate collected from the start of filtration to time t. Since the filtrate must pass through the entire cake, V by A is same for all layers, thus U is independent of A. This is kind of required analysis assumption is required. Filtrate must pass through the entire cake. So, then we have taken only one layer of the cake for this analysis. So, whatever V by A is there, that should be same for all layers, so that the superficial velocity U can be taken as independent of L, that is the thickness of filter whatever the cake thickness of cake or cake thickness. So, now as we know that as the time progresses more and more particles are depositing on the filter medium. So, the mass of solids in the layer that is also going to change with time, right. So, how much that mass is being deposited or what is the mass of solid in that layer of cake of thickness dl that we have taken. So, that we should calculate that, let us say dm. So, then let us say the volume of the layer of cake that we have taken is area of the area is now same as the filter area, filtration area, because in entire the filtration area particles are being deposited, right. So, that area multiplied by the thickness of cake layer that we have taken, that will give you a kind of volume of that particular cake layer, and then if you multiply that one by 1 minus epsilon, that will give the volume fraction of that 1 minus epsilon is nothing but volume fraction of the particles in that layer. So, that will give a kind of volume of particles. 1 minus epsilon A dl is nothing but volume of particles, and then if you multiply that one by the density of particles, you will get the mass of the particles that are present in that layer of a cake of having thickness dl. Okay. So, now this equation we can substitute in equation number 2 and simplify to get this equation. So, this is equation number 2. In this equation what we are going to do, only in place of dl we are going to write dm divided by rho p 1 minus a. This is what we are going to write in place of dl, and then rearrange it, so that whatever this rho p is there, and then 1 minus epsilon would be there, a is already there. So, this actually here 1 minus epsilon whole square is there. So, that square and then this 1 minus epsilon is cancelled out. So, that finally, we get this equation dP is equals to K1 constant, whatever 4.17 is there, that we can take it as K1, because whatever 150 is there in the flow through packed bed constant 150 is there, that is also based on some kind of experimental observation which best suiting to the tortuosity factor, etc. So those constants may slightly change. So not necessary to stick to those constant value as it is. Now henceforth we can take this constant whatever is there as a kind of K1. Okay, K1 is nothing but 4.17 if you compare equation number 2. So K1 mu u 1 minus epsilon Sp by Vp whole square divided by rho p A epsilon q dm is nothing but pressure drop across that layer of a cake of thickness dl that we have taken, right. This equation is valid for low pressure drop filtration of slurries having uniform particles, right. In RHS of this equation 5, except this dm, rest all other parameters are independent of L. All other parameters are independent of L. So that what we can do, we can directly integrate this equation 5. When you integrate this equation 5, then you will get a kind of required equation between pressure drop and then the properties of particles and then void fraction of cake, etc., surface to volume ratio of particles, etc. In those kind of terms we get a equation for pressure drop, right. So now incompressible cakes. So these cakes are in general can be compressible or incompressible cakes. Whatever the cake resistance is there, that is independent of the pressure drop, and then that is not going to change with change in the L, then we can call such cakes are a kind of incompressible cake, but in general most of the cakes are compressible only. So we see both what is incompressible cake and then compressible cake right now. So let us start with the incompressible cake. Same picture we take whatever we have taken previously here. So if you equation 5, if you integrate, we can get this equation integrating. Now this whatever the layer that we have taken is within the cake only. This layer is there, that is within the cake only. So what are the limits of the pressure that, because now initially this equation you have developed for dl. For dl, what is dp you calculated only for this layer, right, only for whatever this layer of cake that you have taken within the total cake of thickness LC at a given time t. At a given time t, the cake thickness is LC. Within that cake we have taken one layer of cake. For this layer of cake, just now we develop a kind of equation for pressure drop. That equation if you integrate it, so you will get this equation. Here the limits for this integration of especially for pressure should be like P prime to PA, P prime to PA, because this layer is there within the cake, and then this integration we are doing only for cake. So the pressure limit should be P prime to PA, and then at P prime, that is when there is no filtration or there are no particles deposited on the surface of filtrate initially, right. So the mass of particles at the interface is almost 0, and then at PA, when the cake builds up and then forms a kind of thickness of LC, let us say whatever the solids are there, the mass of the solids in the cake is MC. So there should be two limits of dm. So 0 to MC. So when you do this one, you get this equation, and then PA minus P prime is nothing but pressure drop across the cake. So that is delta PC. Now filter cake of this type are called incompressible cakes, where we have taken that the pressure drop, the cake resistance, the cake that has formed is independent of a kind of L value. That is, resistance is independent of pressure drop and of position L. So such case whatever the cakes are there, so they are called as a kind of incompressible cakes. Now if you rearrange equation number 6 so that to define specific cake resistance. So actually we now coming to the position where we can describe or develop equation for two different resistance that we have. We have two resistance for the cake filtration cases. One is the cake resistance, another one is the filter medium. So we have arrived to a kind of point where we can measure the cake resistance. How we can measure that? Equation number 6, if you rearrange, whatever this equation number 6 is, this one only, delta Pc is equals to K1 1 minus epsilon Sp by Vp whole square divided by rho p epsilon cube multiplied by mu u mc. So, what have done? So, and then divided by A is there. So, whatever this A divided by mu u mc, or whatever here in equation number 6, if I rewrite this equation number 6, we have delta Pc is equals to K1 1 minus epsilon mu u mc Sp by Vp whole square divided by rho p A epsilon cube. So, out of this one mu u mc by A, whatever is there, that I am taking it to the left hand side, so that I can join with delta Pc as delta Pc A divided by mu u mc, and then keep all other terms in the right hand side itself. So, whatever this delta P A, whatever this delta Pc A divided by mu u mc is there, that is nothing but the cake resistance in terms of the particle properties and voidage. If you wanted to write, this is nothing but K1 1 minus epsilon Sp by Vp whole square divided by rho p epsilon cube. Okay. This alpha, if it is independent of pressure drop dP and then independent of the position L, then we call it as a kind of incompressible cake. So, where here specific cake resistance is nothing but this one. Remember, in the experimental cases, we do not know what is Sp by Vp for unknown particle size and shape in general. Okay. So, we are trying to further simplify this equation, so that without having this information we can calculate this alpha. So, that is what we are going to do now anyway. But in general, specific cake resistance can also be expressed in terms of particle size dP with a different coefficient K2 as below, by simply replacing Sp by Vp by 6 by pi s dP, right. So, then we get alpha is equals to, that constant will be modified, right, whatever 4.17 is there. Now, here that 6 square is also there, right. So, that whatever the new thing is coming, constant is coming, that we can call it as K2. Okay. So, we do not need to worry about what is this exact value of K2. So, let us take that when you on that K1 is combined with this 6 square, then whatever the new constant is there, that we call it K2. So, alpha is K2 1 minus epsilon divided by pi s square dP square epsilon cube rho p. Dimensions of specific cake resistance is a meter per kg. Specific cake resistance is influenced by the physical properties of the cake only, that is what we can say, especially particle size and the porosity. What we can see here from the alpha definition, this alpha is going to be affected by the particle size and then this porosity epsilon along with the density and then sphericity, etc. But this particle size and then voidage is going to have a kind of a strong influence on this one, on the cake resistance. Okay. Now, we take the case of compressible cakes, but in general we know that the cake is whatever the cake resistance is there, that is function of delta P, because as gradually filtration time increases, the cake thickness increases and then the pressure drop increases, right. So, industrial cakes are generally not made up of individual rigid particles, as we have taken in the previous case. We assume that all particles are of same size, as we did assumption in a kind of packed or fixed bed cases. Further, industrial slurries are mixture of agglomerates or flokes consisting of loose assemblies of very small particles, and then resistance of such cakes depends on properties of flokes rather than geometry of individual particles, as been observed by the many experimental results. Okay. So, in the previous case, incompressible cake, what we have seen, alpha is going to be a kind of function of a particle properties, like size of the particle and then voidage of the bed, etc., right. But in general, in reality, the industrial cake, whatever the cake resistance is there, that depends on the properties of flokes rather than geometry of individual particles. And then flokes are deposited from a slurry on upstream of the cake and form a complicated network of channels to which equation of delta Pc does not apply. However, resistance of such a cake is sensitive to method used in preparing slurry and the age of slurry and temperature of material which has been applied for the separation the required filtration process. Such flokes in general are distorted and broken down by forces existing in the cake, and factors like epsilon, K2, Sp by Vp in general vary from layer to layer. Because of that one, pressure drop is also going to be non-linear, and such filtration cake is called a compressible filter cake, where the cake resistance is function of a pressure drop. In such compressible cake, specific cake resistance varies with the distance from septum, that is L, position L, because cake nearest to the septum is subjected to the greatest compressive force and has lower void fractions, and because of that one, the pressure drop or pressure gradient becomes a kind of non-linear. And then local value of alpha may also vary with time in general. Thus, whatever the equation number 6 that have been developed for cake resistance does not apply as mentioned earlier for a case of compressible cakes. That can be applied for incompressible cakes, but for compressible cake that is not applied. But generally, variation on specific cake resistance with time and locations are ignored, and an average value is obtained experimentally for material to be filtered using the same equation, alpha is equals to delta PCA mu u mc for calculation purposes. Okay. So, here only the variations with respect to the time and locations are ignored, but not the variation with respect to the pressure. In order to know the variations with respect to the pressure, what you do for different pressure drops, you do the experiments, you calculate the alpha, and then you can have a kind of a relation between alpha as function of a pressure drop, or you can have a relation between alpha and then pressure drop. So, that will give the compressibility information of these compressible cakes, though we ignored the influence of duration of filtration and then location. Now, filter medium resistance, analogous to cake resistance alpha mc by A, the filter medium resistance can also be defined as Rm is equals to delta Pm by mu u, where delta Pm is nothing but P prime minus Pb. Here typical values of Rm in general ranges 10 power 10 to 10 power 11. So, now we have expressions in terms of maybe pressure drop, we have an expression for the cake resistance as well as the filter medium resistance. Okay. Rm may vary with the pressure drop, Rm may also vary with age and cleanliness of the filter medium, but it is important only during early stage of filtration, as already mentioned, because as the filtration process progresses, more amount of particles deposited, and then cake resistance would be dominating over the filter medium resistance. So, that this may be a kind of important only at the early stage, the filter medium resistance is going to be important only at the early stage of the filtration. Thus, it is safe to assume that Rm is constant during any given filtration, and its magnitude can be determined by experimental data. How to determine this magnitude, that we are going to see. We are going to take some examples to see how to obtain this cake resistance as well as the filter medium resistance. If Rm is treated as an empirical constant, it also includes any resistance to flow that may exist in pipes leading to or from the filter. Now from two resistance one can get the total pressure drop as delta P is nothing but delta Pc plus delta Pm. So from alpha definition delta Pc can be written as mu u mc alpha by A, and then Rm definition delta Pm can be written as mu u Rm, or Rm is equals to delta Pm by mu u. So delta Pm you can write mu u Rm. So when you add these two delta Pc and delta Pm, then you will get the total pressure drop for the system. Here the cake resistance alpha is function of delta Pc rather than delta P, but however in general during important stage of filtration, when the cake is of appreciable thickness, delta Pm is very small in comparison to delta Pc, that is already we know. Delta Pm is going to be important only at the early stage of the process, but later on it may not have a kind of very significant magnitude compared to the delta Pc. Thus, effect of the magnitude of alpha in carrying out the integration of equation number 6, whatever that alpha definition is there, over a range of delta P instead of delta Pc can be safely ignored. Okay, and then equation 11 alpha can be taken as a function of delta P. Okay. So further in equation 11, whatever this total pressure drop equation is there, that is equation 11, it is better to replace u and mc by functions of v and the time t, because volumetric flow rate of filtrate is often measured easily experimentally rather than u or mc. Okay. So let C be the mass concentration of particles deposited on the filter medium per unit volume of the filtrate. Then mass of solids in the filter at time t is given as V multiplied by C, where V is nothing but the volume of filtrate collected. And then further U we already know it as dV by dt by A. So in that equation number 11, wherever u is there you substitute dV by dt by A, and then wherever mc is there you substitute Vc. Then we have this delta P, this is the equation number 11. This part is nothing but your equation number 11. In this equation, in place of mc you write Vc, in place of u you write dV by dt divided by A, and then rearrange this equation so that you can have dt by dV is equals to mu by A delta P multiplied by alpha C V by A plus Rm. Right. In this equation, experimentally the volumetric flow rate or volume of filtrate collected versus time information you can get for a given delta P value. Let us say you take a filter medium and then you take a slurry and then you allow this slurry to pass through this filter medium at certain pressure. Right. So with respect to the time you can collect the volume filtrate and then you can tabulate that one. So that information you know actually, and then viscosity of the filtrate is in general you know, or you can calculate. Area of the filter medium is also known, right, in this equation. So V is known, A is known, right. So this equation if you wanted to calculate alpha and Rm, everything is known except this C. What is this C? How to calculate? Experimentally you cannot measure how much mass is deposited on the filter medium per unit volume of the filtrate, especially during the process of the filtration. Okay. So however there is a process, we can do a kind of mass balance and then we can develop a kind of relation for C. In general for problems they are given straightforward. If they are not given, they should be obtained as like this. Let us assume concentration of solid in the slurry fed to the filter is Cf, and that is less than C. Okay. Because wet cake includes sufficient liquid to fill its pores, the actual filtrate volume V is slightly less than the total liquid in the original slurry, because the entire liquid is not coming as a kind of filtrate. Some amount of the liquid is retained, interstitial space between the particle whatever is there within the cake, that space is occupied by the some amount of the liquid. That is the reason the actual filtrate volume V is less than the total liquid that is present in the original slurry. Okay. Thus correction for this retention of liquid in cake has to be made, and that can be made by the material balance. How it can be made? Let mass of wet cake is mf, which includes the filtrate retained in the voids or the liquid that is retained inside the between the interstitial spaces of particles within the cake. And then mass of dry cake, that is after washing the cake free of soluble materials and drying it, whatever the mass is there, that if you take mc. Then concentration of solids in slurry in kg per meter cube of liquid fed to the filter medium is, if you take Cf. Then concentration of solids in filtrate collected, if it is Cs, density of filtrate is rho. Then by material balance, if you do a kind of material balance and then simplification you do, then you get this C is nothing but Cf divided by 1 minus mf by mc minus 1 Cs by rho. Right. So, this whatever the mf by mc minus 1 Cs by rho is always going to be less than 1. So, this denominator value whatever is there, that is going to be less than 1. So, C is going to be more than the Cf. C is going to be more than the Cf in general. Okay. So, now, so that equation we have this basic equation whatever have dt by dv is equals to mu by a delta p alpha cv by a plus rm. If you operate or if you use this equation for constant pressure filtration, then you have a kind of a methodology to calculate this alpha and rm. Constant pressure filtration, if delta p is held constant, then above equation 13 only variables are v and t, right. So, when t is equals to 0, v is equals to 0 and delta p is equals to delta pm, because when there is no cake formation, whatever the pressure drop is there is that's only across the filter medium. Then this dt by dv equation, whatever this is equation number 13, right. This equation, now if you do a kind of integration, or you take at time t is equals to 0, at time t is equals to 0, whatever dt by dv is there, let it 1 by q naught. So that why are we doing, because we need to have a kind of information for rm and then alpha also. At t is equals to 0, there is no cake formation, so then this alpha is 0. So then what we can write, dt by dv at t is equals to 0 is equals to mu by a dp multiplied by rm, or mu rm by a delta p, that is nothing but 1 by q naught, 1 by q naught. So, this is nothing but from this information, if you know 1 by q naught by some experimental information, you can get the rm value. Substitute this equation 14, this equation back in this equation number 13. So, wherever mu rm by a dp is there, you write 1 by q naught. When you write it, dt by dv is equals to, this is equation number 13. So, dt by dv, now this taking mu by a dp inside. So, mu alpha c by a square delta p v plus mu rm a delta p. So, this I am writing 1 by q naught, mu rm by a delta p I am writing 1 by q naught, and then whatever the mu alpha c by a square delta p is there, that I am writing as a kc. If dt by dv at t is equals to 0 is 1 by q naught. So, at some other instant of time dt by dv we can write it as a kind of 1 by q, or simply you can have this equation as dt by dv is equals to kc v plus 1 by q naught. So, where this kc, if you know this kc information by somehow by experimentally, so you can get this alpha value. If you know this 1 by q naught value somehow by experimentally, then you know this rm value. So, that is the purpose we are doing now. Okay. So, by integration, equation 15 over the limits t is equals to 0 to some instant t, and then volumetric flow rate, initially it is 0 anyway. At time t, if volumetric flow rate or volume of filtrate collected is v, then if you use them as a kind of limits, then this equation number 15 is this one, you integrate this one. So, integration for that purpose dv you take to the right hand side, then if you integrate you have t is equals to Kc V square by 2 plus 1 by Q naught V, and then integration constant that will be anyway 0, because anyway we are taking the definite limit. So, then there will not be any kind of integration constant anyway. So, then here this equation, if you simply rearrange, T by V is equals to Kc by 2 V plus 1 by Q naught. Then T V information you get the experimentally, right. So, experimentally for a given pressure drop, whatever the T V information is there, you rearrange T by V versus V and then plot T by V versus V, then you will get a kind of straight line with intercept 1 by Q naught and then slope Kc by 2. So, from slope you get Kc, and from Kc you get the alpha value, cake resistance, and then from intercept you get 1 by Q naught, and then from 1 by Q naught you can get the Rm, filter medium resistance. Okay. So, this is how now at constant pressure, whatever the experiment that you do, you collect a volume of filtrate with respect to time, that information you can make use to calculate the specific cake resistance and filter medium resistance like this. Now, empirical equation for cake resistance: by conducting constant pressure experiments at various delta P, the variations of alpha with delta P can be found, right. As I already mentioned, if alpha is independent of delta P, then cake is said to be incompressible cake. In general, alpha increases with delta P, as most cakes are compressible at least to some extent. For highly compressible cakes, alpha increases rapidly with delta P. Then under such conditions, if you do experiments at several delta P values and then calculate corresponding alpha values, that if you correlate, you may get a kind of equation like this: alpha is equals to alpha naught delta P power S, where alpha naught and then S are a kind of empirical constants. S is the compressibility coefficient of the cake. If it is 0, then cake is incompressible. If it is greater than 0, it is compressible cake, and then usually for compressible cakes it varies between 0.2 to 0.8. So, whatever the equations till now that we have for compressible and incompressible cake, that is for constant pressure filtration, but batch process. Now, these same equations we can modify or rearrange in a different way, so that the same equations we can use for the continuous filtration, but constant pressure, right. Constant pressure filtration, but continuous process. So, continuous filtration here in cases such as like rotary drum type filters, there are different types of industrial filter equipment are there. So, some of them we are going to see anyway in the next lecture, right. So, one of the type is the rotary drum type filters, where the feed, filtrate and cake move at steady constant rates. All of them are moving at different constant rates, right. So, the cake is also continuously removed, so that the process is not stopped in between just to discharge the cakes, etc. Right. So, such in continuous filtration processes, all these feed coming in, filtrate continue collecting, and then cake removal or discharging of cake is continuously going on as long as the cycle is in a progress. So, for discharging of cake, we are not going to stop the experiment. So, under such conditions, we can call as a kind of a continuous filtration, and then rotary drum type filters are a kind of a continuous filters. Commonly, conditions are transient for any particular element of filter surface, as we know. Example, filter cloth, from the moment it enters the pond of slurry until it is scraped clean once more, it is going to be a kind of function of time. So, this process consists of several steps such as cake formation, washing, drying, discharging, and that each step involves progressive and continual change in the conditions with respect to the time. Okay. So, however, the pressure drop across the filter during the cake formation is held constant. Though the process is continuous, the pressure drop is a kind of held constant. In the previous case, whatever the T by V is equals to Kc by 2V plus 1 by Q naught equation that we developed. There the process is a kind of batch process, okay, but the pressure is constant. Now here the process is continuous, the continuous filtration process, but the pressure drop is again constant. So both of the previously developed equation and this equation whatever we are going to develop for this case are valid for a kind of a constant pressure filtration processes, but one thing, the previous one is for the batch process, and then this is whatever we are going to do is for the continuous process. So since the pressure drop across the filter medium is maintained constant during the cake formation, whatever the discontinuous or batch constant pressure drop or constant pressure drop filtration equations are there that can be used or applied to the case of continuous filters as well with a few modifications. What are those modifications? Actual filtering time is the time for which filter element is immersed in the slurry, and if this is constant, then equation 17 can be rewritten as like this, that whatever the T by V was there, what V was there in the left hand side, that has been taken to the right hand side and then given equation number 18. So that T is equals to Kc V square by 2 plus 1 by Q naught. In the continuous process, what is the volume of filter that is being collected with respect to the time? That is what we are going to check for a constant pressure, right. So this equation now should be solved to get a kind of expression for V as function of time, okay. So here V is the volume of filtrate collected during time t, and then by solving this equation, this quadratic equation, you will get V is equals to minus 1 by Q naught plus square root of 1 by Q naught square plus 2 Kct divided by Kc. This should be plus or minus as per the solution method, but we cannot have a kind of a negative volume of filtrate, so it has to be plus now. If both are minus, then it is going to be negative. That is not possible in real situation. That is the reason we have taken though it is minus b plus or minus square root of b square minus 4ac by 2a form, we have taken only plus here, okay. So here we know what is Kc. Kc is nothing but mu alpha c by a square delta p, and then 1 by Q naught also we know it as mu Rm by a delta p. So if you substitute them here in this equation equation number 19, then we have this equation. From this equation, what you do? You take mu by a delta p common from the both numerator and denominator of the right hand side and strike out, and then after that step you divide both sides of this equation by at. Then you will get this equation, V by at or V by Ta is equals to minus Rm by T plus square root of 2 delta P alpha c by mu T plus Rm by T whole square divided by alpha c, okay. So basically this difference between equation number 19 and 20, that equation number 19 we have in terms of Kc and 1 by Q naught. Here directly we have this equation in terms of alpha and Rm. V by T is the rate of filtrate collected and A is the submerged area of the filter. It is not the total filter area. In continuous process, continuous filtration process, only fraction of filter medium is submerged in the slurry, that we are going to see in the equipment part. Only how much area is submerged in the filter area in the slurry, that is known as the A here in this case, in the case of continuous filtration. Whereas in the case of batch filtration, the entire surface that is exposed for separation of slurries into liquid and solids, that entire area of the filter medium is taken as the area. But in the case of continuous filtration, only the fraction of area of the filter medium that is submerged in the slurry is A. So this equation 20 can also be written in terms of the rate of solids production MC, and then filter characteristics such as the cycle time Tc, drum speed N, and total filter area At, etc. So if the fraction of the drum submerged is F, then A by At is nothing but F. Then cycle time we can write Tc multiplied by f is nothing but the t, which we can also write as f by n, that is the n is nothing but drum speed, and then m dot c for this kind of continuous process we already know that it is c v by t. If you substitute this equation number 21 and 22 in equation 20, or a is equals to f by f a t and then v by t is equals to m dot c by c in equation number 20, then we get this equation. By rearranging simply, this is your equation number 20. Here now in place of v by t you substitute m dot c by c, and then in place of a you substitute f a t. So, and then further you simplify, here you will get left hand side m dot c by a t is equals to this equation. This is much more convenient form of the equation to be used for continuous filtration process, because in general in continuous filtration process this m dot c or n, f etc. are available rather than v and t. If the filter medium is washed after cake is discharged, then whatever the filter medium resistance Rm is there, that is usually negligible. Then that equation number 23, from that equation number 23 if you strike off the Rm terms, then you will have m dot c by a t is equals to square root of 2 delta p c f n by alpha mu. So, these equations 23 and 24, this equation without Rm and then previous equation with Rm terms can be applied for both continuous vacuum filters as well as the pressure filters, though we are writing for the pressure filters kind of thing. So, they are also kind of valid for the kind of vacuum filters. For compressible cake, where specific cake resistance varies with pressure drop according to alpha is equals to alpha naught delta p power s, then this equation 24 can further be modified like this. So, if Rm is negligible, equation 25 predicts that filtrate flow rate varies inversely with square root of viscosity and that of cycle, but in general that is not true based on the experimental observation, especially for short cycle times this is not true, and then equation 23 should be used. Okay. Generally filtration rate increases as drum speed increases and then cycle time Tc diminishes, because cake formed on drum face is thinner than at low drum speeds. Further, at speeds above a certain critical value, filtration rate no longer increases with speed but remains constant, and cake tends to become wet and difficult to discharge. So, finally constant rate filtration. The previous two cases whatever we have, the constant pressure filtration for batch and then continuous processes. Now, we are going to have equations or principles of constant rate filtration under the category of cake filtration. Okay. So, though it is a very rare, we need to have a kind of equations. If the rate of filtrate is constant, then linear velocity u is constant. So, u we can write in rather than dv by dt by a, we can write it as v by at, because now here the rate filtration rate is constant. Okay. And then alpha equation, we have this equation alpha is equals to delta pc a by mu u mc. In this equation mc you can substitute as cv, and then u you substitute as v by at, then we get delta pc by alpha is equals to mu c by t v by a whole square. Here alpha is function of delta pc to account for the compressible cake. When the rate of flow is constant, the previous equation number 27 can be used directly to relate the overall pressure drop to time if alpha is known as function of delta pc and if delta pm can be estimated from experiments. So, in that above equation substitute alpha is equals to alpha naught delta pc power s and use u is equals to v by at in equation number 27. So, this is your equation number 27. So, here alpha in place of alpha, if you write alpha naught delta pc power s, and then in place of v by at you write u. So, then you get this equation. So, and then rearrange, so all delta pc terms you write one side. So, delta pc power 1 minus s is equals to alpha naught mu c t V by AT whole square, and delta Pc is nothing but delta P minus delta Pm whole power 1 by 1 minus S as it is. Assume the filter medium resistance is constant during a given constant rate filtration. So, delta P m should also be constant, because del Rm is nothing but delta P m by mu u. U is constant for a constant filtration rate. Viscosity of filtrate is in general constant. So, if Rm is constant, then delta P m should also be constant. So, this equation we can write it as delta P minus delta P m whole power 1 minus S is equals to KRT, and then Kr is nothing but alpha naught mu c V by AT whole square, right. And then this V by AT, if you write as a kind of U, then Kr can also be written as alpha naught mu c U square. That is about constant rate filtration. The references for this lecture, the entire lecture is prepared from this reference book, McCabe, Smith and Harriet, Unit Operations of Chemical Engineering. There are other reference books where you may find some information as well. Thank you.